Hey there, it's Max. In this module, we're going to be talking about the House of Force. The House of Force is actually one of my favorite techniques. I think it's really clever in how it works, and I just enjoy that. So let's get into it. House of Force is a technique that gives you an arbitrary right to an arbitrary location, which is really cool. Even Unlinked, which was an arbitrary right of sorts, had its limitations. The House of Force was first talked about in Malik Maleficarum, which is a pretty famous Frack article. If you've never read it, I really do recommend reading it. It is pretty cool. This article talks about 4 different heap exploitation techniques, including the House of Force. I'm gonna have to remove my camera for a bit for these slides. So the technique has to do with the top chunk. If you remember the top chunk, it is the leftovers of the SBRK allocation done after we create the heap. You need to know how big this is because in the future it may need to extend it. Now the only thing we actually care about the top chunk is the size. Everything else shouldn't be used. The prev size, FT, and BK aren't used. The only thing that should be used is the size. That makes sense because it's more so just a representation of the rest of the heap, at least the rest of the allocated heap. If you remember reading and going through the ordering part of this module, which seems like forever ago, there is the top chunk usage and the extend to heap with SBRK call. We are trying to abuse this functionality right here. I'll show you what the code looks like for that in a moment. So when you use the top chunk, if nothing's available in the bins, then it will try to use the top chunk. And if there's room in the top chunk for the allocation that we need, then it will try to take data from it. The way that this works is it will shrink the top chunk, as you can see with the green arrows that got smaller. And when it does this shrinking, it creates this new chunk and gives that information or that pointer to the user. And everything else is just the top chunk, once again. Now, I think this code here is fairly interesting because it's actually pretty simple. So this is the code that actually does this writing process where it's shrinking the top chunk. Here, victim is a pointer to the top chunk, as you see by the AV top that it's referencing, which is going to be a pointer to the arena. The size is the size of the top chunk that it is getting, and it uses the same chunk size macro as all other chunks. And the NB is the amount of memory that the user has asked for malloc. And if the size of this chunk is less than the allocation we're requesting, or really, do we have enough in the top chunk, then it does this if statement. And this is the usage of the top chunk route. If that wasn't true, then it would have to extend the heap or find some other way to allocate it. Now, within that if statement, this is the code that's there. It does size minus NB, which is going to be the size left over for the allocations for the top chunk. So we're doing size minus NB, and then NB is going to be the size of the chunk that's going to be given back to us. So when we subtract that, that's remainder is what's left over for the top chunk to use. So it's going to use that new size. It's going to then move itself forwards by using the chunk and offset macro by those NB bytes. And finally, it sets that to be the pointer to top. So that's all that that's that entire functionality for setting up the top chunk. So this is where it gets fun though. What if we altered the size of the top chunk to bypass this check? If we had this size for the top chunk be astronomically big, let's say it's 64 bits of Fs, then this would always fail, meaning that it would give us back a chunk at an arbitrary location, which is pretty awesome. So the attack is, if we change the size of the chunk, the top chunk to be in particular, to be extraordinarily large, we can get the top chunk to point to an arbitrary section in memory, so that later on, when we do an allocation, we write to that spot that we want to. So visually speaking, if we corrupt the top chunk, this is what we're left with. We have this top chunk that looks infinite in size. We've corrupted it to go beyond the end of the heap here. It goes beyond the end of the heap. And then all the way past libc, past the stack, past all the good stuff. So now, if we allocate this, we effectively have a primitive that allows us to arbitrarily move the top chunk pointer. So when this top chunk pointer moves further down, we can put it in libc, we can put it in the stack, we can put it wherever we want. At the end of the day, this technique is about moving that top chunk needle to go to any location we want. So the flow of the attack is first we corrupt the size of the top chunk. After that, we allocate a very large section directly in front of our target and hope it doesn't get fully written to. And after we've done that allocation, or that very large chunk is close to it, then we need to do one more allocation to overlap with the target. Now, what actually makes a good target in this case? But before we talk about that, we're going to talk about how to actually go about doing this. So step by step now, and with a little bit more detail. First, we need to extend the size of the top chunk to overlap with other sections of memory. Right now, if we say these green lines are the entire size of the top chunk, then that's all we really see. And if we try to allocate beyond that, then it does the SBRK allocation to extend the heap further. But if we extend that, notice how this goes beyond that section. Now, when we do that allocation, it goes too far. In order to do this, you could have a use after free or a buffer overflow or something that just allows us to edit the top chunk. In practicality, you can set it to all ones. You can set it to whatever values you want. It just needs to be a ludicrously sized value. And if you set it to be 64 bits of values, then you can effectively wrap it all the way around if you want to. So the next part of this is allocating it close to the target. So again, the goal, if our target is in libc, our goal is to move this top chunk needle downwards to be close to our target. So what actually makes a good target? Of course, anything with function pointers is always good. So libc has some interesting function pointers. The stack has return addresses. The God entry. There may be a function pointer on the heap. You can even wrap all the way around to the heap completely, which is pretty crazy. But our target for this is going to be the malloc hooks. So although I think in the newest version of libc they finally got rid of this, it still exists in most things. So malloc has function pointers that allow you to overwrite where it's going to. This is really helpful for debugging, performance analyzing with things like mcheck and mtrace. And what these do is when you execute free or malloc or these other functions, when it calls it, it will first check to see, hey, is this pointer set? And if it is, then it will redirect to some other code. But in that code, you can also redirect to the original malloc, and it works fine. There are various pointers. There's malloc hook, free hook, realloc hook, after more core. The more core hook is a pointer for a wrapper around SBRK and mmap. So a lot of really interesting stuff going on here, though. The malloc hooks are awesome for hijacking control flow. The free hook is the best because we control an input parameter. For instance, if you can get a function that has the same declaration as free, it's really easy. For instance, system takes in a string as input, and the free hook takes in a single pointer as input as well. If that happens to be a string that at the very beginning of it, then we can execute an arbitrary command, which is really cool. But things like the malloc hook and also work as well. But the malloc and free hooks have been abused forever, and they're really, really cool things to hit. If you've loaded your binary in GDB, you can usually just do print underscore underscore free hook in order to get the pointer for it. So the next step to this is allocate close to the target. In our case, we're going to say we want to overwrite the malloc hook. And when we overwrite the malloc hook, we want to allocate a size very close to the target. And the reason we want to go close to, we'll talk about in a minute, so just forget that question's in your head for right now. But we want to go from the target to the top, or from the top chunk to the target. So the math for this is we need to use target minus top chunk. Using this, we can move the needle, as I was saying before, to the proper location. The other day, this is an address, and this is an address. So if we just do target minus top chunk, we get that difference. And that difference is how much we move the needle. In actuality, we need to subtract hex 20 to deal with the metadata of various things, because we're going to allocate one thing on the top chunk, and then we're going to allocate one thing close to our target, like I mentioned. So the actual size you want to do with is going to be the target address minus the top chunk address minus hex 20. And if we allocate something of this size, then we literally just move the needle. So once we get it close to the target, our needle has now moved, and we're now ready to overwrite the target. So once we're at that point, we just do one more allocation of that particular chunk size, and it goes right over the top of it. And once it's over the top of it, the top chunk moves a little bit further, but we've already done our damage. We've allocated over the top of the malloc hook and can write a function pointer to that location. So to remember, recap, we're moving this needle. That's the main thing. And we're moving that needle by changing the address, by using the size of the chunk we're going to be allocating. Now you're probably wondering, why don't we just overwrite the target in the first place? And that's a really good question. There are cases where that does work. However, you cannot write to unmapped memory, and that's where this problem comes into play. So it's very unlikely you're going to have a primitive that's going to allow you to write to an arbitrary index, and that's it. So in this case, it's really nice because we can assume that if we say, hey, we need X amount of bytes, but we only write to a few of them, then the allocation is still going to stay. And so we can make it so that the contiguous buffer overflow is not something we need. You can just do it in one allocation. That's fine too, but this is the more likely situation where you can only write a few bytes, not have it crash, and then allocate directly after that in order to allocate over your target. So that way you completely miss this gap right here. If you try to write to that gap, it's gonna crash the program. So in order to do this technique, you need to overwrite the size of the top chunk first. After that, you need control over the chunks sizes that you're going to be allocating. That's a pretty tough thing, especially with these very, very large sizes that are kind of unreasonable. It's difficult to get that situation. You also need known location for the heap and whatever your target is. If you're overwriting something else on the heap and you wrapped all the way around, which you actually can wrap with this, which is kind of a cool part of the technique, then you wouldn't need that, but in a lot of cases you still do. So when you view this in Pwnedebug, you can look for top chunk. There's actually a top_chunk command that will give you information about where the top chunk is at and such. But there's also the main arena top, which you can view as well. That gives you a little bit more information about it. Notice how these values are the same. So that's how I would look for that information in GDB. So that is the House of Force. To recap, the first part is about corrupting the top chunk. After you've done that, you need to allocate a very large section directly in front of your target. And to finish the exploit, you need to overlap the chunk over the top of your target. So this is one of my favorite techniques. I think it's really cool that we're abusing this code right here that is checking to see if the top chunk's too big. It's big enough to handle this. By overwriting the size, we can make it think it's way bigger than it really is, and it wraps around. I just think it's a really clever technique, and can't believe how early on this was covered. Cool. I'll see you in the next video.